Hi there, welcome to my lesson on static equilibriums and torque. So we're going to go ahead and run along with this. I am in fact wearing my little Cavaliers warm-up jersey here. Big win last night, you probably don't care, but it was against the New Jersey Nets, Kyrie, and anytime you can beat Kyrie in his flat earth world, I'm happy. Hey, let's get to work. So let's see here. We have this scenario where there's some sort of industrial sort of bench. It's 10 meters long, it's like 33 feet long, and it weighs 200 kilograms. That's just the steel bench itself. And it has some sort of package or box, or let's say some sort of industrial press on it that's 100 kilograms. And so the table itself is 10 meters long. The press is 7 meters from the one edge. So of course it's also 3 meters from the other edge. And what I want to do is I want to actually make it so that way, I can actually tap on it, here we go. I actually want to make it so that way this location here actually has the ability to rotate. And you're like, why would it rotate? There's two legs and the whole bit. And well, what if you kicked out that leg? Then it would rotate, wouldn't it? And so that's what you have to do with these kinds of problems, is you have to pretend as though one leg has the ability to get kicked out. You see, what I want to do is I want to determine just how much force there is with each one of these legs. Okay, so what if I'm building this table and I want to figure out how strong each leg needs to be? Or what if instead of them being legs, what if instead we had some sort of cable, right? It was hanging from the ceiling. There's like a cable on each side. How strong does the cable need to be? And I'm sure you can kind of see where the application of this would be. So let's go ahead and run through this and figure out how much force is acting on each of the legs. Okay, so what do we have going on here? Well, if I am going to in fact take out this leg, let me do this for a moment. Let me actually kind of kick it out. And let's look at what is happening. So the table itself does in fact have a torque that is applied. It is a torque that is applied about its center of mass. So I'm going to say that's about the center. So that, of course, is going to be about 5 meters from the one end. So from this axis of rotation here, I'm pretending that it can rotate there. From the axis of rotation, the torque that is applied at the moment that I kick this thing out, the torque that is applied, right, the torque that is applied, my tau symbol always is really terrible, I'm sorry, is equal to the force times the perpendicular distance. So it's the force, which is mg, times r. So I'm going to call this object 1 just for argument's sake. And so the torque of object 1 is equal to the force of object 1 times the radius or lever arm distance of object 1. So an object in which gravity is pulling on it and causing it to rotate, you always measure to the center of mass of that object. Okay, that's where the force is being applied. It's as if gravity is pulling all of its force on the object right there at the center of mass. And you're like, well, doesn't gravity pull on the whole thing? Yeah, it does not pull only on the end. That is the often mistake that's made, is people will take the entire measurement of the entire table. But you look, gravity is pulling on every single little bit of this table, and on average, it's pulling on the middle. So at the middle, there is the force of object 1 acting down, which is, of course, equal to m1g. So this actually is m1g r1. So that is the torque that is being applied in this sort of like counterclockwise sort of direction. And the torque does change as it were to go down, but we are only concerned about that first moment in time. Okay, so let's look at this other object. What is the torque that is applied by this other object? So in this case, we have this distance of 7 meters. So to the center of mass, and I'm just going to put a dot here, at the center of mass, it's being pulled down, and that is, of course, going to be, we'll call this object 2. So the torque that is being applied is going to be the force, right? So, in fact, let me put the tau symbol again. See if I can make it look a little bit better this time. Not really. So the torque is equal to, this is the torque of object 2. That's equal to the force acting on object 2 times its radial arm length. And this, of course, is equal to m2g times r2. Okay, so that's the torque. Now notice that both of these torques are acting in a clockwise, right? A clockwise sort of fashion. And I'm going to say that clockwise is a negative direction, and I am going to say that anything that acts in the opposite direction, counterclockwise, is going to be a positive direction. Now I like to do that because of coordinate planes, right? Whenever you have a xy, this is an x down here, xy coordinate plane, you put your fingers in the direction of the x, curl your fingers in the direction of the y, right? Positive angles, and then right hand rule, the thumb points towards you, and so that's why the z-axis, right, points out of the page towards you. But that's maybe a lesson for another day. So generally speaking, positive angles are counterclockwise. So let's keep that to be a nice consistent thing. Okay, so let me move these little references up here. Okay, so what I want to do is I want to make this statement. So just like how you have with any other circumstance, Newton's second law, right? The sum of all forces in any particular direction, let's say the x direction, is equal to ma in the x direction, which is then in turn equal to whatever you get from your free body diagram. So that's going to be like, force 1 plus or minus force 2 and so on. I'm going to use this same format, but for torque, a rotational force. So instead of saying all this, I'm going to say the sum of all torques is equal to, let's see, that's equal to I alpha. And since there is no rotational acceleration actually happening because I have this, I'm not actually kicking it out, I'm going to put it back. And so what will this be? Well, this means that this whole thing is equal to 0, right? So I could have done the same thing here. If there's no acceleration, right, we would make that thing equal to 0. Okay, so now let's look at our free body diagram that we've got going on here. So what do we have acting in the positive direction, and what do we have acting in the negative direction? Well, let's look at the negative direction first, since I've gone over that. So here I have the torques that I specified right here, but they are acting in a negative direction, right? So this is acting in a negative direction. It's going clockwise. And so we're going to say this is a negative M1 GR1. And then what else do we have? Let's see, we have this torque that we had specified as well, and that also is acting in a negative direction because it wants this whole system to rotate in that direction. So that's a negative direction when you're talking about rotation. So that's minus M2 GR2. Do we have any other torques happening in that same direction? Let's see, there's the table itself. No, we already accounted for that. There's this box that wants it to rotate in this clockwise fashion. And there's no other forces causing it to want to rotate about this pivot point. There's no other torques causing it to want to rotate in that direction. However, there is a force here. In fact, let me choose a different color. Let's choose blue. So we have a force here, right? There's a force, and I'm going to call this object 3. Okay, so there's a force. In fact, let me specify it as a torque, right? So there's a torque that is equal to the force of object 3, right? This is the torque of object 3. This is the force of object 3 times the radial arm length of object 3. And so in this case, it's not gravity, so I cannot substitute mg in place of the F. But this force, this is what I'm actually trying to determine. So what is R3? Well, R3 is actually the distance, the length of the entire table. So, and notice that this is wanting it to rotate in the opposite or counterclockwise direction, or anti-clockwise direction if you are a little bit more of the British terminology. And so I'm going to say plus the force of object 3 times the radial arm length of object 3. Okay, I think we're good. So I'm just going to focus on this part here because that's the part that I need, right? So 0 equals all this stuff. And let's see, I know the masses, I know the R's, I know the G. Okay, let's just kind of solve for F and then solve. So let's do that. So let's move the variables around so that way F is alone. So that means that the force of object 3, which is acting up, that's the pillar, that is going to equal, let's see, we have M1 M1GR1 plus M2GR2 all over R3. All right, so I added this to each side, added that to each side, and then divided by R3. And so if we put in our values, let's see what that gets us. So let me kind of pause real quick. That way we can actually do this quickly. All right, so let's take a look at what I've got here. So I've gone ahead and put in the numbers. I even color-coded it a little bit. So here we have the values for M1GR1. This is the torque caused by the table itself, plus the values for the industrial press or whatever it might be. So that's the M2GR2, right? This right here, and then divided by R3. Okay, so that's all color-coded. And then when we put in our values, what do we get? So let's see here. I went ahead and did the calculation. Maybe you can kind of see what I did there. So the 200 times 9.8 times 5. Then I took that and added it to 100 times 9.8 times 7. All right, get the numerator, and then divide it by 10. So it looks like I did everything right, and we have 1,666. What an evil little table. So 1,666. Let's go ahead and write that in. So this is going to equal 1,666. What are the units? That's a really ugly 6, but excuse me. And that's going to be newtons. 1,666 newtons. And so that's how much force is being applied up right here. Okay, that's the force. That's the force of object 3, right? This is the pillar. I'm going to call this pillar over here object 4. Okay, so I got the force being applied by the pillar on the right. Do I have to do the same thing, this whole process on the left? I could treat this as if this is a pivot point. You know, if I knock out this guy, then I would have to look at all the torques that are being applied this distance, and I can go through the whole process and figure out how much force there is on the left. And I can totally do that. It would work, but it's not the easy way. In fact, now that I have now that I've gone ahead and figured out the force on the right, I can make it much simpler. Remember this whole process here? Let's do that. So the sum of all forces equals, let's see, I'm going to look at the y direction, the vertical direction. So I have, let's see, we have acting down, we have the force of the table. I'm going to put a T there. I'm going to say that's down, so I'm going to treat down to be a negative direction, minus the force of the, let's say, the press, right? Or in fact, let me use my numbers that I denoted. I don't know why I'm doing the letters. Object 1, object 2, and all that bit. Okay, so we have the force of object 1 acting down, right? That's the press, minus the force of object 2, the press, right? Object 1 is the table, object 2 is the press. Sorry if I misspoke. Plus the force of object 3 acting up, which is this leg, plus the force of object 4, which is also acting up. So I actually have numerical values for all of these things except for the fourth one. And the whole thing is equal to ma, isn't it? But it's not accelerating, so it's 0. So let's go ahead and set all these things equal to 0, and let's solve for object 4. So that means, let's see, let's add F1 and F2 to each side, and then subtract F3. So that means that F4 is equal to, let's see, F1 plus F2 minus F3. And so what are those things? Here, let me kind of make sure that I've got my, I'll be all right. So what do we have? Let's see, F4 is going to be F1. What's F1? That's mg, isn't it? So that's m1g plus m2g. Let's see, minus, what's F3? Oh, we said the 1,000, I'm just going to leave that as F3 for a moment. That's the 1,166. So all I have to do is take mass 1 times g. So mass 1 is the 200 kilograms. This is M2, this is the 100 kilograms, and then this is the 1,666. Let's go ahead, I'll pause, and we'll run that calculation real quick. Okay, let's go ahead and just put this in together. So we have M1 is the 200 kilograms times 9.8. Okay, so with that, we're going to add, let's see, m2g. So that's going to be plus the 100 kilograms times 9.8. And then we're going to subtract F3, which is 1,666 newtons. So that should do it. And so we have a value of 1,274. It's good that it is a positive value. That means that it is acting in the up direction, which seems about right. So that is going to give us 1274. So this is equal to 1274 newtons. So we are just using Newton's second law that in the vertical direction we have these forces acting up, and that counteracts the forces acting down. So this is essentially the fundamentals of statics, and I'm sure you can see where the application goes from here. So let's hide this thing off to the side. Bridge building and all that sort of thing, and then hopefully you guys can see the other applications. So if I were to kind of like throw something out there, let's say for example, what about an awning? So you have a building and there's some sort of awning that wants to get put onto the building. So just some sort of structure, and then there's some sort of steel cable that is put onto the building. So let's do that if it'll let me. Right, so it has a steel cable that connects somewhere here, something like that, and so the awning, right? In fact, let's change the color of the awning. I'm going to make this quick, but let's change the color of the awning real quick. So it's a beautiful red awning, whatever. And so from the center of mass, this awning does in fact want to rotate. So typically you'd probably consider that to be the axis of rotation. If the cable were to break, it would want to pivot there. So let's say that the force of gravity is acting. Whoops, did not mean to make that erroneous sort of arrow. Oh, it did it again. So from the center of mass, there's a force acting down, and so from there we have mg acting down. Okay, and let's see what else we have. Well, this force acting up. So the distance at which it acts, let's say this is the distance here about which the cable acts. So I'm going to say that's the value of r for the cable, and let's say that this is the distance r1 for the awning. And so we would take, let's see, we can break down the forces in terms of what's happening with the cable. Okay. And so the cable is applying a force in that direction, but what if we were to break that down into its x and y components? So there's clearly a component of force that way and a component of force that way, right? And so it is the vertical part of the force times this distance that would give you the torque acting in this direction. So you can do that to figure out how much tension there is in the cable, and then you can do the same thing in order to figure out just how much force there is acting up here against the wall at this pivot point. In fact, if you were to do it right, what if you had friction, right? You could have a friction force acting up in this direction. You have a force, this force here is causing this thing to be pressed up against the wall. That would be the same as your normal force. And it's possible for you to have enough friction up against the wall to where there's actually no need for an actual pivot point, or an actual connection point there, I should say. Of course, you would never do that, but it is possible to do it. So if you were to take like a ruler and tie a string to the ruler, you can make there's a certain angle at which you can actually pull the string taut and actually make it so that way the ruler does not slide out from the wall. So, if I were to press this up against my hand, if I lay off a little bit, you can see it starts to slide. And so there's a certain amount of force needed that I needed to press before it slides out. So so there's lots and lots of applications here. One of those applications is like a ladder, and it slides out. At what angle can you put a ladder here? And I think we'll save that for another time. And so I think this is a good intro to statics, which is basically civil engineering kind of stuff, and it actually has lots of interesting applications. Remember that the acceleration is always 0. sum of all forces, sum of all torques, it's 0. So, hope this clarifies some things and gives you something to think about, and you guys have a good one. Next time.